In this video, we will discuss the Quicksort algorithm. Quicksort is one of the fastest algorithms for sorting elements in an array. Sorting is one of the foundations of data structures and algorithms, so you should know the intuition behind this algorithm very well. So, in this video, I will give you a line-by-line simple intuitive explanation of all the code that we will be writing. My name is Aditya Shenoy from Brainy, where I make programming simple and fun. YouTube statistics show that some of you who watch my videos are not subscribed to this channel, so if you end up liking this video, please consider subscribing. It is free and you can always change your mind in future. Quicksort is a divide and conquer algorithm. In this algorithm, we pick a pivot element and arrange the other elements in such a way that the elements that are lower or lesser than the pivot element is positioned to the left of the pivot element, and the elements that are greater than the pivot element is to the right of the pivot element. We will see this with an actual example once we write this code to understand this better. So we will start by defining the function. We will name it as quicksort. This function will just take the input array that we want to sort. So quicksort array. As quicksort is a recursive algorithm, the parameters needed for the actual quicksort implementation is more than just one parameter of array. So we need to take help of a helper function. We will name it as quicksort helper, which will take parameter of the original array, the left bound and the right bound, or the lower bound or the higher bound. So the left bound will be 0 initially. So to sort the entire array, we want to specify 0 to length of array minus 1, like this. And once we have sorted that, we can return the array. Remember, if lists are passed inside the function parameter, then it is passed as a reference and not by value. So a single copy of array will be passed inside this function, and this inside which this will be sorted. And so this array variable, once this function is returned, will be sorted array. Now we can start defining this helper function. So define quicksort helper. As discussed, it will take three parameters: the array, the left bound and the right bound. As discussed, this function will change the original array in such a way that the pivot element is placed in its correct position, and the elements lower will be to the left and elements greater will be to the right of the pivot element. And as you can see over here, the elements lower to the pivot element is present to the left, but they are not sorted. So we need to call this function quicksort helper recursively for these subarrays BAC and XZY. But eventually what will happen is we will keep on dividing this subarray into two halves, and eventually it will lead to a subarray of 0 or 1 element. An array with 0 or 1 element is already sorted. So if left is greater than or equal to right, which means there are 0 or 1 element, this equal to is when the left bound and the right bound is the same, that is only one element is present in the array. In that case, we do not need to do anything. So we will just simply return. And then we need to find the pivot position. This pivot position is the correct position of the pivot element. As you can see, if this is the input array, after one recursive call of this quicksort helper, this m variable will move over here, that is it in its correct position. So we need to find the upper bounds of the lower subarray and the lower bound of the upper subarray. So we need to find this position, and this position will be returned by a function partition, which we will define in some time. And this function will again take the same number of parameters: the array, the left bound and the right bound. And once we get this pivot position and an array, as again this array is passed as a reference, so we do not need to return the array. The array variable will again be updated in itself. So once we get this position m, we can call this quicksort helper recursively for these two subarrays. So after this pivot function, the partition function, we will call this quicksort helper With the same array will be passed everywhere, just the bounds are changing. So the bounds of the this sub array will be original left and pivot minus 1. And for the second sub array will be same, but the lower bound will be pivot plus 1 and the original right bound. Notice we have not included this pivot position, pivot minus 1 is included and pivot plus 1 included because M is already sorted as M is in its correct position. So this is the entire quicksort helper. As you can notice now, the entire sorting process, the actual sorting process will happen inside this partition function. And this quicksort helper is just for calling this recursive function and to check for this base cases. So now we can define this partition function. As discussed, it will take the same number of parameters, array, left and right. Now we can select any starting pivot element from this array, it doesn't matter, but for simplicity of the code, we will take the rightmost element of this array, the element that is present in the right bound, so that we can traverse the elements from left to right like this and check the relative position of these elements with respect to the pivot element. So we will initialize the pivot to right, the right bound, and for traversing the elements from left to right, we will initialize the variable I equal to left like this. So we will start traversing the elements from left, and while I is less than pivot, I'm using a while loop instead of for loop because you will come to know once we proceed with the code that the increment that will happen inside this loop to the I counter is not consistent. That is, for some iterations the I can get incremented, but for some the I will remain the same. And for loop is not a suitable choice of loop when the increment to the loop variable is not constant. So while I is less than pivot, so this less than pivot indicates that we need to process all the elements before the pivot. Now you might wonder why we are not putting the variable right instead of this pivot. This is because the pivot position is going to change as this pivot element is going to shift to left, and once we shift this, the elements to the right is already sorted, so we do not need to check for elements after the pivot even if the pivot has moved left. So we will stop when I reaches pivot, and when I equal to pivot, we will be in a position where this I will be over here, so we can break out of the loop. So inside this loop, what we will do is we will check if array of I, that is ith element in the array, is greater than the array of pivot. What we are doing essentially is we are checking for the first iteration I will be over here and the pivot element is this. So we will check if this element is should be to the left side or to the right side of this pivot element. And if it is to be the right side, then this condition will be true because array of I is greater than array of pivot. And if this is the case, now comes the intuition part. So to move this letter or move this element to the right of the pivot element, we do not have anything to swap it with. So for that case, what we need to do, we need to create a position for that. And if you think from another perspective, once this X is shifted over here, the M's position will be over here. So this C position, that is the element just before the pivot element, has to be moved around. So to resolve this, what we can do is we can cycle this 2 and this element in a cycle. So after this iteration, what we want is The rest of the elements, that is b, z, y, a, will remain the same, but the c, the character c, the element c should go over here, m should go over here, and x should move to the right of the pivot. In that case, we have moved the character x to the right of the pivot element, which is right. M is moved to the left, which is also right. But the character C, we do not know whether we should move it to the left or not. So for that reason, we will keep the I counter over here only. We will not increment the I because this element is not yet resolved. But the pivot has moved to the left, and so the pivot element can get decremented. So we need to do two things over here, that is cycle three elements, that is array of I, the element before the pivot, that is array of pivot minus 1, and the pivot element itself. And in the position of array of I, we need to put the element that is behind this array of pivot. So array of pivot minus 1. In the position of the array of pivot minus 1, we want the pivot element. So like this. And in the position of the pivot, we want the ith element. So array of I. And the I variable will not get incremented, but as we have moved the pivot element one index back, we can decrement the pivot element. So this is one case where array of I is greater than array of pivot. As you might know, there are three conditions for the equality or the comparison. One is greater than, one is equal to, and one is lesser than. For now, we will assume that this array will contain unique elements. We will discuss what will happen if the elements are duplicate in this once we complete the code. So for now, we will discuss only the greater than and lesser than. So for lesser than, that is the else condition, that is in the next iteration. For example, we want to compare this elements, that is the element C and the element M. Unlike the previous case, the element C is already in correct position with respect to the pivot element M. That is, C is less than M, so it is already present to the left side of the pivot element. So we do not need to do any swapping as in this case. So we know that this element is resolved as compared to this. So we can move to the next character. So inside this else clause, we will increment the I variable. And we do not need to do anything over here. So what will happen eventually is the I will get incremented, and the pivot index, the pivot position will get decremented, and it will reach this configuration where pivot and I will occur in the same position. And uh, in that case, we can break out of this while loop and return the pivot position, because this pivot position is required for these two recursive calls. So this is the entire implementation of the quicksort. We can test this by calling just the quicksort, because the helper function will be called automatically. Quicksort, just putting random numbers and running this. Yes, 2 3 5 6 8, we will get a sorted array, but this is happening like a black box. So we need to understand, like, at least for one iteration, what is happening and how the indices are changing. So just give me a second, I will enter some debugging statements so that we can visualize the status of the variables inside this while loop. So in these four statements, we have entered the debugging remarks. So instead of doing manipulations for debugging inside the original array, we are creating first the copy of the original array. This slice operator with just the colon creates a copy of the array in this debug. And to mark the elements that are present in the ith index and pivot, we will mark this with I equal to and pivot equal to, like this, so that we can visualize which variable, which element is this index I and pivot is pointing to. And then once we are done with this, we will wait for user input, print this debug, and as we are putting string elements inside this list, we will get unnecessary quotes, so we will replace that with nothing. So this is just to visualize the state of the variables. These four lines are optional. I will comment this out once we have done the dry run. So let's run this. So the first call of this partition will have the entire array. The array and bounds will be from 0 to length of array minus 1. So the I position will start from the leftmost bound, that is I equal to 2, and the pivot element as discussed will be the rightmost bound. So pivot will point to this, the rightmost element, that is 3. So this I equal to 2 is lesser than the pivot equal to 3. So this condition will become false and it will just simply increment the I, because we do not, the element 2 is already in correct position with respect to the pivot 3. So we are just incrementing the I like this, pivot will remain the same. Now I equal to 5. So the element is 5, element is greater than pivot. Now we will enter, this condition will become true and we will enter this if condition. Now these three elements will be swapped. Which three elements? I equal to 5, pivot, and the element behind the pivot. So 5, 6 and 3 will get swapped, as in 6, 3 and 5. So 5 will go over here, 6 and 3 will be shifted. 8 will remain the same. So 8's position is not changing. We are just cycling these three uh, in a clockwise fashion, if that makes sense. So pivot 3 will go over here, 6 will go over here, and 5 will loop back to over here. Let's see this. So as you can see, I equal to 6, pivot equal to 3 and 5. So this is the swap statement, and we have decremented the pivot. So pivot was originally in the last position, now it is in the second last position. But we have not changed the position of the I, because after swapping this element is yet unresolved, but the phi element, the element phi is now resolved with respect to pivot 3. So again the element 6 is greater than 3. So again these three elements will be swapped, 6, 8 and 3, and it will lead to 8, 3 and 6 like this. Again pivot will get decremented by 1, I will remain the same. Now again the ith element is greater than the pivot, but in this case there is no element behind the pivot, or I should say there is, the element behind the pivot is same as the ith element. So what this statement now will do is, this statement array of I equal to array of pivot minus 1 will not do anything, because essentially I and pivot minus 1 are the same. So this statement will not do anything for this iteration. So array of pivot minus 1 will get the value of array of pivot, and array of pivot will get the value of array of I. So in short, these two elements will be swapped. Instead of 3 value cycling, it will just swap the 2 values. So once this is done, this value, the pivot will get decremented by 1, and so the while loop will break, and so this debugging information will not print. And so the final positions you can see 2, 3, 8. The 8 and 3 elements are swapped, but the next iteration has start. That is for I equal to 8 and these range. It has returned. So what we can see over here, the pivot element, the pivot index of 1. If we are considering zero-based indexing, this is 1. Pivot of 1 is returned over here, and these two recursion calls are called with left and pivot. So if you see, there is only one element in to the left of the pivot element. So this is one of the base cases over here. That is, if left is equal to right, we do not need to sort an array with just one element. It is already sorted. So we are returning. So this partition function is not called, as you can see over here. But for the right array, this partition function has been called. So this process will continue with the new pivot. Now is 5. So it will sort everything eventually. So I hope that you have understood this with this one iteration. So I will interrupt this and comment these statements, the debugging statements, so that it just returns the final output. Now we can test this for boundary cases, that is for empty array, it should return empty array. For an array with just one element, it should return the same array because it is already sorted. Now there are some questions that we need to ask when considering a sorting algorithm. The first question is whether this sorting algorithm is stable or not. We can convert any sorting algorithm to a stable sorting algorithm. By stable sorting algorithm, I mean that if there are two elements with the same key, then their relative position in the sorted array should be the same as in the original array. Let me demonstrate that with an example. So if I have an array with 1, 1 and 2, this one after sorting, let me consider a different example like this. So this will get sorted to 1, 1 and 2, 2. But which one is to the left and which one is to the right, same for 2, that determines the stability of the sorting algorithm. So if after sorting this 2 is to the left of this 2 and this one is to the right of this one, then it is a stable sorting algorithm. You might wonder why this is important, because these are essentially the same elements. This happens when the key is not the entire element of the array. So in this case, what we have done is we have essentially kept the keys, that is the element that we are sorting on, that is the first element of each of this tuple, the same as this example. But now this will make a difference if this one B is to the left of this 1A, because these are not now the same elements. So a stable sorting algorithm will return a output. So if the keys are same, that is 1 and 1, the original position, that is this 1A is to the left of the 1B in the original array, so that should retain in the final output as well. Same goes with 2A and 2B. 2A should be to the left of 2B if they are equal. Unfortunately, this implementation that we have done is not stable, but we can convert any sorting algorithm to a stable sorting algorithm by including two keys at a time. That is the original key. If we consider this 112 example, we can convert this entire sorting algorithm to a stable sorting algorithm if we incorporate the indices of it as well. So we can put this condition, that is if these two elements are equal in this elif part, elif the elements are same, the ith element and the pivot element are same, we can look into their indices, and before swapping, before doing this, we need to change this, transform this original array to make this table. So what I essentially mean is this original array will get converted to a enumerated form of this original array. So before applying the sorting algorithm or calling any other function, this original function should convert this original array into something like this. So this will add the indices of the original array, the original element. So 0, 1, 1, 2, 2, 1 and 3, 2. And in this elif part, which I will not write because that will just complicate this thing, and as we have assumed that this element will not be a compound element like this, it will just be the simple element. If they are equal, that is these elements are equal, one and sorry these and these, so this is the element, this is the index, so this one and this one is equal. So if they are equal, the tiebreaker should happen between these two, the indices, the original indices. So this tiebreaker will assure that the element that was originally to the left will remain in the left, and vice versa for the right side as well. So we can convert this by just changing the key and the tiebreaker condition by adding a tiebreaker condition over here, but the entire implementation will remain the same. The average and best case time complexity of the quicksort algorithm is O of n log n, as in both these cases the array is partitioned in equal halves. For partitioning the array in equal halves, the pivot element selected should be the median of the array. But in the worst case, the pivot element selected is the maximum of the array. And so the left partition will contain all the elements except for the pivot, and the right partition will be empty. Due to this uneven partition, the worst case time complexity becomes O of n squared. The space complexity is constant as we are doing swap operations in the original array itself, which is termed as in-place sorting. And so no extra space is required apart from the recursion step. So quicksort is a good option if the input array is large. Quicksort should be applied on arrays and not linked lists, as indexing elements from linked list is not a constant time operation. That is indexing over here. So if we try to apply this same concept for the linked list, this array of I, array of pivot minus 1 and so on will not be a constant time operation anymore. So for linked list, we should use merge sort instead. If this video has helped you understand the quicksort algorithm intuitively, please do give this video a like, comment any feedback that you have for this video or this channel, share this video with your friends. The code that I write in all my videos of this channel is available in my GitHub profile, whose link is in the description. You can connect to me via LinkedIn, whose link is again in the description. If you want to see a line-by-line explanation of data structures and algorithms like this, check out the playlist over here. If you want to learn Python built-in functions along with various Python features, tips, tricks, and real project examples, then check out the playlist over here. If you want to see a hands-on game development project, check out the playlist over here. And I will see you in the next video.